Hey there, junior engineering apprentice. Welcome to today's explainer. I am absolutely thrilled to have you here in the workshop with me today. We've got a massive goal, getting you completely prepped and ready to absolutely crush your Grade 8 Technology Common Exam. Think of me as your mentor, and together, well, we're going to demystify the incredible world of engineering. So grab your notebook, get comfortable, and let's get building. Okay, here's the blueprint for our time together today. 1. Forces, pushes, and pulls. 2. Building strong shapes. 3. Making machines move. 4. Why things break. And finally, 5. The engineer's design challenge.
Section 1. Forces, pushes, and pulls. Right, so before we can actually build anything, we need to understand our invisible enemies. Forces. A force is really just a push or a pull on an object, and they're constantly, and I mean constantly, attacking our structures. If we don't understand them, our buildings will literally just fall down. Let's start with a really fundamental one, tension. Tension is a pulling force that stretches something. If you were explaining this to a 5-year-old, you'd probably just tell them to think about stretching a rubber band across their fingers, right? Or playing a super intense game of tug-of-war. That pulling, that stretching feeling, that's tension in action.
You can literally see tension traveling through a tightrope as it's being pulled. But tension is just one of 4 main forces you absolutely need to know. There's also compression. That's a squashing force, kind of like sitting down heavily on a really soft cushion. Then there's torsion. Torsion is a twisting force, like when you wring out a wet towel. And finally, shear. Shear is a sliding force where parts are pushed in opposite directions, exactly like how a pair of scissors slices right through paper.
Okay, let's do a quick check here to test your new skills. Think about those 4 forces we just talked about. What force occurs when you take a screwdriver and you forcefully twist a screw deep into a piece of wood? I'll give you a second. Got it? Yep, it's torsion. You're applying a twisting force directly to that metal shaft.
Section 2. Building strong shapes.
So, now that we know about the forces trying to basically tear our stuff apart, how do we engineers fight back? Well, the secret lies in strong shapes. Think about a standard horizontal beam carrying weight across an empty space, using vertical columns to transfer that weight straight down to the ground. It works, sure, but when we build a roof, we use angled pieces instead. When a piece is being squashed together in compression, we call that a strut. And the piece at the very bottom holding it all together, the one being pulled in tension, that is called a tie. The absolutely crucial point here is choosing the right shape. And this is exactly why engineers are completely obsessed with triangles. We call it the power of triangulation. Seriously, if you build a square frame and push the side of it, it just completely collapses into a wobbly mess. But a triangle is perfectly locked. The forces are shared evenly by the 3 sides, making it incredibly, incredibly stable.
Section 3. Making machines move.
We've mastered stationary structures, so let's bring our designs to life with some dynamic movement, because, machines actually need to move to be useful. Let's look at gears. Gears are really just wheels with teeth. The driver gear, that's where the movement starts, like your bike pedals. Then you have the driven gear, which receives that motion. But here's the absolute golden rule of gears. When 2 gears touch, they always spin in opposite directions. If the first turns clockwise, the next one turns counterclockwise. To fix that and make them spin the exact same way, we just pop an extra gear called an idler gear right in the middle.
Movement isn't just about spinning, though. In technology, we categorize 4 distinct types of motion. Linear motion goes in a straight line, like an elevator going up. Rotary motion spins in a circle, like our gears or, say, a helicopter blade. Reciprocating motion moves straight back and forth, or up and down, kind of like a sewing machine needle. And finally, oscillating motion. That swings in a curved arc, just like a playground swing. But what if you have a motor that spins, but you actually need something to bounce up and down? Well, you need a motion translator. And a cam is exactly that. Here is how it works, step by step. First, the axle rotates. Second, the oval-shaped cam spins right along with it. Third, a little rod, called a follower, rests right on top. As the wide high point of the oval comes around, it pushes that follower up, and as the flat low point comes around, it drops back down. Boom. Rotary motion is magically converted into reciprocating motion.
Now, cams are amazing, but they have a really tough cousin called the crank. A crank also turns rotary motion into reciprocating motion, but they do totally different jobs. A cam is perfect for light tasks with very specific timing. Think of like a little toy wooden bird popping its head up and down. But a crank? A crank is tied directly to a rod to push and pull with raw, heavy power. You need a crank for heavy tasks, like handling the immense force pushing the pedals of your bicycle.
Section 4. Why things break.
All right, put on your hard hat and grab your magnifying glass. It's time to do a little engineering forensics. Because despite our absolute best efforts, sometimes the forces just win. When a structure can't handle a load, it fails. There are 3 classic failures you need to know. First, a fracture. That's when a material just snaps right in half, like a pencil. Then, buckling. That's when something is squashed under compression until it just folds in on itself, like a plastic drinking straw. And finally, toppling. That's when a structure simply loses its balance and tips completely over, like a giant tower of toy blocks. To prevent this kind of disaster, engineers read structure diagrams so they can spot weaknesses way before they actually build. And you can do this in 5 easy steps. First, identify the type of structure. Second, find the supports resting on the ground. Third, locate where the heavy load is actually pushing from. Fourth, trace how that weight travels through the frame. And fifth, identify if the pieces, the members, are acting as struts in compression or ties in tension. Let's analyze a roof structure together using those exact steps. The load here, let's say it's a super heavy pile of snow sitting on top. That weight pushes down hard, creating compression on those angled wooden struts. They're literally being squashed. But the horizontal piece running right along the bottom, remember, that's our tie. It's experiencing tension, pulling super tight to stop the bottom of their roof from just spreading completely apart under all that weight. Okay, be the detective for a second. I want you to actively analyze this. If that snow is pushing down on the very top of the roof, where does the load travel to safely reach the ground? Give it a think. Yes, it travels down the angled struts, outwards to the corners, and straight down the brick pillars on the sides, which act as the supports holding the whole thing up. Awesome job. Section 5, the Engineer's Design Challenge. Okay, it is time for your final test. Combining forces, shapes, and motion into a single real-world design challenge. But hey, before an engineer ever touches a hammer, they have to draw. We use a very specific language of lines so other builders don't get confused. Thick, dark outlines show the visible outside edges of an object. Dashed lines are hidden detail lines, showing secret parts tucked away inside. Long and short dashed lines are center lines, showing symmetry or the exact middle of a hole. And lines with arrows on the ends? Those are dimension lines, telling us the exact size. Just picture a 3D block for a second. The dark, thick outlines make the actual shape pop out at you. Then you might see dashed lines tracking a hidden tunnel running right through the inside of that block. The dimension lines with the little arrows prove the exact length of the object so you don't mess up the cut. And a center line running straight through the middle of a circular hole, that shows you exactly where to drill. All right, here is your challenge. You need to design a mechanical toy hammer for a child. When someone turns a handle on the side, the wooden hammer needs to automatically move up and down. Based on what we learned today, turning a handle is rotary motion, but the hammer needs reciprocating up and down motion. What mechanism would you put inside this toy to make that actually happen? Think back to our motion translators. You'd need a cam or a crank. Exactly. But hold on a second. Evaluate the wooden stool supporting our toy hammer. Right now, it's basically just a square frame. If a kid cranks that handle really, really fast, the whole thing is going to wobble and eventually collapse. How would you suggest using what we learned about strong shapes to fix it? Hit the nail on the head. You would use triangulation. You draw a diagonal piece of wood, a tie or a strut, straight across those legs to turn that wobbly square into rock-solid triangles. And the whole shebang comes together. You have officially mastered the forces that pull at our world, the structural shapes that defend against them, the mechanisms that create dynamic motion, and even the language of engineering drawings. You are entirely ready to ace your technology exam, but honestly, more importantly, you have the actual blueprint to create something amazing. So my final question for you is, what world-changing machine are you going to build next? Thank you so much for joining me on this explainer, and I will see you next time.